Ever feel that jolt, that sudden shift right into your feet?
Yeah.
It's not just you, it's the Earth.
It's a constant reminder.
That we're living on this, well, giant moving puzzle.
Mm-hmm.
And for all of human history, well, that motion, it's kind of been a challenge.
Absolutely.
How do we build on ground that, well, that isn't entirely stable?
Yeah.
Today, we're diving into this world, the world of earthquake engineering,
Oh, fascinating.
exploring how humanity went from this fear and superstition to actually understanding
Mm.
and even preparing for, like, the awesome power of earthquakes.
It's a pretty remarkable journey.
Yeah.
From simple trial and error to, the complex math and this cutting edge technology we use today.
Right. And we've got excerpts from a fascinating book here that takes us, like, through this whole history of earthquake engineering.
Oh, wow.
It's all about the math, the methods, the trials, and the triumphs
Right.
of securing uncertain ground.
I like that.
So where do we even begin?
Well, before, equations and formulas entered the picture, early builders, I mean, they just relied on observation
Right.
and experience.
Yeah,
they
right.
they noticed that, wider bases and certain materials, they seem to work better.
Right.
But imagine they were designing without a true understanding of why.
That's mind-blowing.
It is.
Building a house without knowing why some designs are more stable.
Yeah.
It'd be like trying to fly a plane
Right.
without understanding aerodynamics.
Exactly.
Talk about a leap of faith.
It is. But then during the Enlightenment, there was this pivotal shift.
Okay.
Earthquakes were no longer seen as, the wrath of gods.
Uh-huh.
They were recognized as natural phenomena, like governed by the laws of physics. This opened the door to, scientific inquiry.
Sure.
And crucially, measuring.
Enter the seismograph, right?
Absolutely.
That must have been a game changer.
Oh, absolutely. Finally, there was a way to move beyond just like anecdotal evidence, right, and start collecting hard data.
Right.
This led to the development of scales like the moment magnitude scale,
Okay.
which quantifies an earthquake's energy.
Okay. So now we can measure how powerful an earthquake is.
Right.
But how do we translate that into its impact on buildings?
Right.
How do we go from understanding the energy of an earthquake to actually designing structures that can resist it?
That's where seismic waves come in. These
Yeah.
are the vibrations that radiate outward from the earthquake source.
Okay.
And they're not all created equal. You have P waves,
Okay.
which are compressional waves. They travel fastest. Then there are S waves. They move side to side, and they're known for their destructive potential. And finally, you have surface waves rolling along the Earth's surface. Each type interacts with structures differently,
Right.
leading to this complex dance of forces that engineers must understand.
So knowing the energy of an earthquake and the types of ways it generates,
Yeah.
engineers can then begin to design buildings that can withstand those forces.
Right.
It sounds like a monumental task.
It is. It is. And that's where building codes enter the picture.
Yeah.
They're essentially a set of rules and guidelines based on scientific understanding
Sure.
and, importantly, lessons learned from past earthquakes.
So they're constantly evolving,
Exactly.
learning from each disaster,
Yeah,
each failure,
right.
and incorporating those lessons into the next generation of buildings.
Precisely. Early building codes were fairly basic,
Okay.
but they've become incredibly complex over time.
Yeah.
They now incorporate like detailed equations and procedures to ensure that buildings can resist those seismic forces.
I imagine things like the weight of the building,
Sure.
the materials used, even the type of ground it's built on, all play a significant role in those calculations.
Absolutely. All those factors contribute to how a building will respond during an earthquake. Engineers use a formula to calculate something called the design base shear.
Design-based shear.
Yeah. Think of it as the minimum lateral force a building needs to resist.
Yeah.
This formula takes into account the building's weight,
Right.
the seismic response coefficient, which considers the building's period of vibration, and the anticipated ground acceleration.
Period of vibration. So a building has its own rhythm.
In essence, yes. It's the time it takes for a structure to complete one full cycle of back and forth motion.
Mhm.
Taller, more flexible buildings tend to have longer periods,
Okay.
while shorter, stiffer buildings have shorter ones. This becomes crucial when we consider the concept of resonance.
Resonance. That sounds ominous.
It can be. If the building's natural period of vibration matches the dominant frequency of the ground shaking, you can get a dangerous amplification of movement.
So it's like pushing a swing at just the right moment. Each push adds more energy,
Yeah.
making the swing go higher and higher.
That's a great analogy. And just like a swing set to its own rhythm, a building can be sent into a dangerous sway during an earthquake,
Right.
which is why engineers work hard to avoid that scenario,
Sure.
adjusting a building's mass or stiffness, or even incorporating damping devices.
Damping devices. Now we're talking about some seriously cool engineering solutions, right?
Yeah, they're pretty remarkable.
I've heard about things like base isolators and tuned mass dampers.
Yes.
They sound almost like science fiction.
They're pretty remarkable feats of engineering. Base isolators are essentially giant shock absorbers placed under a building's foundation.
Okay.
Imagine a building sitting on these massive flexible pads that can absorb much of the ground motion during an earthquake.
So instead of the building shaking violently along with the ground,
Right.
the base isolators, they act as a buffer,
Yes.
allowing the building to move more gently,
Exactly.
kind of like a car suspension system,
Mm-hmm.
smoothing out a bumpy ride.
Exactly.
And then there are tuned mass dampers.
Right.
Picture a large weight placed at the top of a building, carefully designed to move in opposition to the building's sway.
Right. It counteracts it.
So it's like a counterbalance,
Right.
working to stabilize the building
Exactly.
during an earthquake.
Mm.
It's incredible to think how engineers can use physics to like choreograph
It's amazing.
a building's response to these powerful forces.
It truly is a testament to human ingenuity.
Yeah.
But it's important to remember that all these advancements, they wouldn't be possible without learning from past earthquakes.
Right. Every major earthquake, while tragic, provides invaluable lessons.
Absolutely.
It's like each event pushes the boundaries of our understanding,
right.
revealing new vulnerabilities
Mm.
and inspiring new solutions.
And that's what makes the history of earthquake engineering so fascinating. It's a story of constant learning
Right.
and adaptation, driven by a desire to protect lives
Mm-hmm.
and build a more resilient world.
Okay. So let's dive into that history.
Let's do it.
Where should we start? Which earthquakes have had the biggest impact on the field?
Well, to truly appreciate how far we've come, we need to go back to the beginning. Remember those early builders, the ones relying on like observation
Right.
and experience.
That's just throwing things at the wall and seeing what sticks.
Pretty much. Imagine trying to design a safe structure without any understanding of the forces at play.
Right.
It's mind-boggling.
Yeah, it's like trying to like bake a cake without knowing what flour or sugar is.
Exactly.
Just throwing ingredients together, hoping for the best.
Exactly. But that's how it was for centuries. Then, with the Enlightenment, came this shift in thinking. Earthquakes weren't like supernatural events anymore. They
Yeah.
were natural phenomena governed by laws that could be studied and understood.
And that understanding opened the door to actual measurement,
Mhm.
to the development of tools like the seismograph, and eventually to the equations and models we use today.
Precisely. And those models are fascinating. At its core, securing a building against earthquakes, it comes down to understanding how forces act on structures and how those structures respond. Every time the ground shakes, it's trying to push or pull a building in different directions.
That's like an invisible hand trying to knock it over, right?
Exactly. And to resist those forces, engineers rely on fundamental principles of physics, starting with Newton's second law of motion. Force equals mass times acceleration. You might remember that from high school physics.
Vaguely. Something about objects at rest, wanting to stay at rest.
That's inertia. And it's definitely related. But Newton's second law tells us that the heavier something is, the more force is required to make it move or accelerate. So when it comes to buildings, the mass of the building itself plays a significant role in how it will respond to earthquake forces.
So a heavier building needs to be designed to withstand greater forces. Makes sense. But what about the materials? I imagine they play a huge role too.
Absolutely. Different materials behave differently under stress. Think about a rubber band versus a piece of uncooked spaghetti.
Okay.
The rubber band can stretch and bend without breaking,
Right.
but the spaghetti snaps easily.
Right. Some materials are more flexible, others more brittle. It's all about how they react to stress.
Exactly. And that's where elasticity comes in. It describes a material's ability to deform under stress and then return to its original shape. When the stress is removed,
Right.
engineers use a value called the modulus of elasticity. to quantify this property.
Hmm.
Steel, for instance, has a much higher modulus of elasticity than rubber,
Right.
meaning it's much stiffer and harder to deform.
So a steel beam can withstand a lot more force before bending or breaking.
Yeah.
Compared to, say, a rubber beam of the same size, it's like the difference between a twig and a steel rod.
Precisely. Now, to make things a bit more manageable,
Okay.
engineers often simplify complex structures into simpler models. One common approach is to represent a building as a system of masses connected by springs and dampers.
Wait, springs and dampers, like what you'd find on a car suspension? We're talking about like shock absorbers for buildings now?
You got it. Think of the springs as representing the stiffness of the building's structural elements,
Okay.
like columns
Ah,
and beams.
right.
The dampers represent the building's ability to dissipate energy, much like shock absorbers smoothing out bumps on the road.
So they're taking the energy from the earthquake and
Right.
converting it into a less destructive form, right?
Right.
It's like letting the air out of a balloon slowly instead of letting it pop.
That's a great way to think about it. Now, using these simplified models, engineers can apply equations to calculate how a building might move and vibrate during an earthquake.
Okay.
And one important concept here is the building's natural frequency,
Natural frequency.
which is essentially the rate at which it would naturally oscillate or sway back and forth if disturbed.
So it's like a building's inherent rhythm,
Yes. Yeah.
its own unique way of moving.
Yeah. And you mentioned resonance earlier. That's when things can get dangerous, right?
Right.
Resonance occurs when the building's natural frequency matches the dominant frequency of the ground shaking.
Uh-huh.
This can amplify the building's movements dramatically, leading to greater damage or even collapse.
It's like pushing a swing
Okay.
at just the right moment, adding more and more energy with each push until it goes soaring. But in this case, it's a building we're talking about. So that kind of soaring is not a good thing.
Exactly. That's why engineers try to avoid resonance
Mm-hmm.
by adjusting a building's mass, stiffness, or damping properties.
Right.
They might change the dimensions of structural elements, use different materials,
Mm.
or add more damping devices.
So it's all about finding the right balance, making sure the building can ride out the earthquake without shaking itself apart.
Uh-huh.
That's a delicate dance, isn't it?
It is. But of course, buildings aren't simple systems with a single frequency. They're complex structures with multiple floors, walls, components that can all move in different ways. And that's where things get a bit more complex mathematically.
Okay, here's where my brain starts to hurt a little.
Yeah.
We're talking about matrices
Yeah.
and multi-degree of freedom models now, right?
Yes. But the basic idea is to break down the building's movement into different modes of vibration.
Okay.
Imagine it like musical notes, each with its own frequency and shape, representing how different parts of the building move relative to each other.
So instead of trying to analyze the entire building's movement all at once, they break it down into smaller, more manageable chunks. It's like solving a puzzle, one piece at a time.
Exactly. This makes the problem much more solvable. Engineers can then use these modal analyses to predict how the building will respond to different types of ground motions.
So they're creating a sort of like earthquake fingerprint for each mode, and then combining those fingerprints to predict the overall response. It's like building a 3D model of the building's movement during an earthquake.
That's a great analogy, but it doesn't stop there.
Okay.
Engineers have developed even more sophisticated techniques, like nonlinear time history analysis.
Okay, this sounds intense. What is that?
Imagine playing back an earthquake in slow motion,
Okay.
observing how the building reacts at each moment.
Okay.
Nonlinear time history analysis allows engineers to simulate how a building would respond to a specific recorded earthquake, or even a simulated one.
So they're running virtual crash tests for buildings, using real earthquake data to see how they hold up. It's like a video game for engineers,
Yeah,
but with incredibly high stakes.
that's a great way to think about it. And these simulations are incredibly powerful. They allow engineers to consider things like the nonlinear behavior of materials.
Nonlinear behavior. You mean how like a steel beam might start to bend permanently if the forces are strong enough?
Exactly. In real earthquakes, materials don't always behave in a perfectly predictable way. They can crack, yield, or deform permanently. And these nonlinear behaviors can have a significant impact on how a building performs during an earthquake.
So these simulations are crucial for understanding how a building will actually behave in a real earthquake,
Hmm.
taking into account all those complex variables.
Precisely. It's about getting as close to reality as possible.
It's incredible how engineers use these tools
Hmm.
to create buildings that can withstand the immense forces of an earthquake. But we haven't even talked about like all the amazing innovations in materials and devices that are like pushing the boundaries of seismic design even further.
That's right. We've touched on base isolators
Right.
and tuned mass dampers. These innovations are remarkable examples of how engineers are using physics to not just resist earthquakes,
Right.
but to actually control how buildings move during those events.
Okay, let's dive into those a bit more. I'm particularly fascinated by how these systems work. Can you explain the difference between base isolators and tuned mass dampers,
Oh,
and how they're actually implemented in buildings?
okay. Let's start with base isolators. Imagine a building resting on a system of large rubber bearings and steel plates.
So instead of the building being like directly connected to the foundation, it's sitting on these giant rubber pads.
Yeah.
Is that what's isolating it from the ground motion?
Exactly. These pads are designed to be very flexible in the horizontal direction,
Okay.
allowing them to deform and absorb a significant portion of the energy from the earthquake.
So it's like placing the building on a cushion
Hmm.
that absorbs the shock. Does that mean the building doesn't shake at all during an earthquake?
It still moves, but the base isolators dramatically reduce the forces transmitted to the structure. Think of it like a boat on waves.
Okay.
The boat still moves up and down, but it's not being slammed against the ocean floor.
That's a great analogy. So the
Mhm.
building might sway a bit,
Mm.
but it's a much gentler motion.
Right.
Less like being in a washing machine and more like rocking on a boat.
Precisely. That gentler motion translates into less damage and a lower risk of collapse.
Amazing. So what about tuned mass dampers? How do those work?
Tuned mass dampers, or TMDs, they take a different approach. Instead of isolating the building from the ground motion,
Right.
they're designed to counteract the building's own swaying.
So they're like built-in stabilizers
Right.
working against the building's like natural tendency to wobble during an earthquake.
That's a good way to put it. Imagine a large weight, often several tons, suspended near the top of a building.
Yeah.
This weight is connected to the structure with springs and dampers,
Mm-hmm.
and it's carefully tuned to oscillate at a specific frequency.
So when the building starts swaying during an earthquake,
Uh-huh.
this giant weight swings in the opposite direction,
Yeah.
working against the movement. It's like a counterweight, right?
Yeah. Exactly. It's like a pendulum swinging out of sync with the building's motion and this counter movement. It helps to reduce the building's overall sway,
Okay.
minimizing damage.
That's incredible. But I imagine these TMDs must be very precisely designed.
Hmm.
You can't just hang any old weight from the top of a building and expect it to work, right?
You're right. It requires careful engineering calculations to determine the optimal weight, spring stiffness, and damping properties for each specific building and location. But when it's done correctly, a tuned mass damper can dramatically reduce a building's movement during an earthquake.
It's amazing how these innovations leverage physics
Yeah.
to create safer structures.
Yeah.
It's like engineers are choreographing a building's response to an earthquake.
Yeah.
But we've talked a lot about the science and engineering
Yeah.
behind earthquake resistant structures.
Right.
What about the real world events
Mm-hmm.
that have shaped this field? What can we learn from the history of earthquakes?
Well, the history of earthquake engineering is a fascinating one. It's full of tragic events, but also incredible stories of resilience and innovation.
Right.
Each earthquake, while devastating, has provided invaluable lessons that have helped push the field forward.
So let's talk about some of those pivotal moments.
Mhm.
Which earthquakes have had the biggest impact on how we design and build
Yeah.
in earthquake prone areas?
Well, one of the most significant events was the 1906 San Francisco earthquake.
Oh, wow.
It was a turning point for understanding how buildings respond to earthquakes. Before that, construction was largely based on tradition and experience, not on a deep understanding of the forces involved.
So it was less about science.
Yeah.
And more about, well, this building stood up last time.
Yeah.
So it should be fine.
Exactly. The sheer scale of the destruction in San Francisco, it forced a rethink. Engineers started to realize that flexible structures, particularly steel frame buildings, they performed much better than rigid ones, especially those made of unreinforced masonry.
It's a reminder that sometimes it takes a disaster
Mm.
to spur innovation.
Yeah.
What about other examples where tragedy led to breakthroughs?
The 1923 Great Kanto earthquake in Japan is another important one. This earthquake highlighted the importance of city planning in seismic safety. It's not just about individual buildings,
Mm.
but how the entire urban landscape can be designed to withstand an earthquake.
So we're talking about wider streets for evacuations,
Mm-hmm.
fire breaks to
Yeah.
stop blazes from spreading,
Yeah.
and more resilient infrastructure overall.
Right.
It's a holistic approach to earthquake preparedness.
Precisely.
Yeah.
The devastation in Tokyo and Yokohama led to significant changes in how cities were designed and built, with a greater emphasis on seismic safety.
It's amazing how these events force us to reimagine what a city can be.
Yeah.
What about more recent earthquakes? Have they taught us anything new?
Definitely. The 1964 Alaska earthquake,
Okay.
one of the most powerful ever recorded, provided a wealth of data for scientists and engineers.
Wow.
It was so strong that it was recorded by seismometers worldwide.
Wow.
This data revolutionized our understanding of how seismic waves travel through the earth,
Right.
and led to better hazard maps, which are crucial for predicting where and how strong shaking might be in the future.
It's like the planet gave us this massive data set to study. Talk about a real world experiment.
It is.
But it's not just about the shaking during the earthquake, right?
Right.
What happens afterward is just as important.
You're right. Post-disaster investigations,
Yeah.
they're crucial. Think of it like a forensic investigation,
Okay.
but for buildings.
Wow.
Engineers, they study the damage patterns
Hmm.
to understand why some structures failed and others held up.
So they're looking for those telltale signs, those weak points that can be improved in future designs.
Yeah.
It's about learning from mistakes,
Hmm.
even if those mistakes are tragic and costly.
Precisely. For example, the 1971 San Fernando earthquake, it revealed that the way reinforced concrete columns were being built
Uh-huh.
was a major vulnerability. The steel ties holding the concrete together weren't strong enough.
Right.
It showed how even seemingly minor details in construction can make a huge difference.
It's a great reminder that strength isn't just about the materials themselves.
Right.
It's also about how they're put together. Are there other examples of these like aha moments from past earthquakes?
The 1985 Mexico City earthquake is a prime example.
Okay.
This one really emphasized how soil conditions can amplify ground shaking.
Oh.
Mexico City is built on soft clay,
Yeah.
and during the quake, it was like the whole city was bouncing on a giant bowl of jelly. The damage was far worse than anyone anticipated.
That's a sobering thought.
Yeah.
So the same earthquake in a different location
Mhm.
with different soil
Yeah.
could have a completely different outcome.
Mm-hmm.
It's a reminder that context matters.
Exactly. It underscores why site-specific assessments are so important in earthquake engineering.
Right.
You need to know what's under the building,
Right.
not just the building itself.
It makes perfect sense. You wouldn't build a house on sand if you knew a hurricane was coming.
Yeah.
So how are all these lessons from the past
Mm-hmm.
being put to use today?
Mm.
Are we simply incorporating them into updated building codes, or is there more to it?
Building codes have definitely become more comprehensive and
Mm.
sophisticated, but it goes beyond that. We're seeing things like performance-based earthquake engineering becoming more common.
Right. This is about designing buildings, not just to avoid collapse,
Right.
but to stay functional
Right.
after an earthquake.
Yeah.
It's a whole different level of thinking.
It is. Imagine using computer models to simulate how a hospital would fare in a major quake. You're not just looking at whether the walls stay up. You're thinking about whether critical systems like power and water will keep working,
Right.
so the hospital can still serve patients.
That makes a lot of sense.
Yeah.
Especially for critical infrastructure.
Yeah.
And I've also heard about these amazing early warning systems. Are those becoming a reality?
They are. Imagine getting even a few seconds of warning
Right.
before the ground starts shaking. That's enough time to take cover for automated systems to shut things down and prevent damage, and for emergency responders to be ready.
Mm.
We're also seeing more more structural health monitoring,
Okay.
where sensors can detect damage early on.
So it's like giving buildings a checkup
Hmm.
to make sure they're still in fighting shape,
Yeah,
even after a tremor.
exactly. It's all about using technology to make our buildings smarter
Right.
and more resilient. It feels like we're moving towards a future where earthquakes, while still a force to be reckoned with, will have less of a devastating impact.
It's truly remarkable how far we've come from fearing earthquakes as acts of gods to using science and engineering to build a safer world. But it's not just about the science, is it?
Right.
It's about the human stories, the
Absolutely.
resilience,
Yeah,
the innovation, the constant drive to learn and improve.
absolutely. The history of earthquake engineering is a testament to human ingenuity
Okay.
and our determination to protect lives and create a more resilient world. And it's a journey that continues. We're always learning, innovating, and striving for a future where we can live with less fear
Yeah.
and more resilience in the face of these powerful natural events.
So for you listening, here's something to ponder. With all these incredible advancements in earthquake engineering, how do you think cities of the future will be designed? What role do you think technology will play in making our world safer from earthquakes?